Today we'll be talking about message authentication. We're continuing our discussion of integrity. Message authentication codes are another way to provide message integrity. So a message authentication code is a keyed cryptographic hash function. This is a hash function in which the hash value that is output depends on the input value and on a secret key. The data flow looks like this. You have some message, that message gets input to the MAC, the message authentication code, along with a key, which is also input to the MAC function. And the output is called a tag. So this is the hash value. And when we're talking about keyed hash functions, we use the term tag to refer to the hash value. Here's a simple protocol using a message authentication code. Alice has some message she would like to send to Bob. She computes the tag of that message. Alice and Bob share a secret key, K. Alice computes the tag of that message using a message authentication code and sends to Bob both the message and the tag. Bob also knows the secret key. When Bob receives the message and the tag, Bob recomputes the MAC, the keyed hash function over the message, to check that it matches the tag that was sent on the wire. If an attacker tries to modify the message en route, the MAC that Bob computes will not equal the tag that is sent on the wire. And because the attacker does not have access to the secret key, the attacker cannot produce a new valid tag after modifying the MAC. Some of the properties of MACs, or the two properties of MACs that we would like, are authentication and integrity. Authentication is about providing assurance of the identity of the sending party. So this is authentication of data origin, and this is provided by the secret key. With message authentication codes, the sender and receiver share a secret key. So the receiver, upon receiving a message with a valid MAC, knows that only someone in possession of the secret key could have produced the MAC. And note that this was not a property of cryptographic hash functions, in which the hash algorithm is well known and anyone can provide a hash of a message. As with cryptographic hash functions, however, MACs also provide integrity. Once the MAC has been computed, the message cannot be modified without invalidating the MAC. And some particular message authentication codes algorithms are HMAC, CBC-MAC, and CMAC. HMAC is a construction that uses a key with an underlying collision-resistant cryptographic hash function. So HMAC SHA-1 or HMAC SHA-256 are examples of an HMAC. CBC-MAC and CMAC have a different construction. These combine a block cipher with a secret key. And in practice, CBC-MAC is slow and it's not often used, and CMAC improves upon the CBC-MAC construction. So how can we fit the pieces together? We've talked about providing confidentiality, and now we've talked about providing message authentication. But what if we want both message authentication and confidentiality? There are three possible ways you might want to combine encryption with a keyed cryptographic hash function, so combining encryption with a MAC, in order to provide both message authentication and confidentiality. And we'll talk about all three of these. The first one is encrypt and authenticate. So separately encrypt and authenticate. So here's the setup for encrypt and authenticate. Alice and Bob share two symmetric keys. So this is not a public key pair, right? These are two separate shared secret keys. In this scenario, Alice has a message that she would like to send to Bob. She first encrypts the message using key K1 to produce the ciphertext C. She separately computes the MAC of the message using the second key, K2, and this produces the tag. Alice then sends the cipher and the tag on the wire to Bob. The ciphertext and the tag on the wire to Bob. When Bob receives the ciphertext and tag, Bob can first decrypt the ciphertext to retrieve the message, and Bob does this using the shared secret key K1. Then once Bob has retrieved the message, Bob can check the integrity of the message using a MAC algorithm with the shared secret key K2. Bob will compute the MAC of the message and verify that it matches the tag that was sent on the wire. This this construction is not in general secure. In the general case, it does not provide message authentication and confidentiality. And the issue is that the hash, the tag, is sent in the clear. And just like hash functions, MACs are not necessarily providing confidentiality. So sending that tag value in the clear is problematic and could violate confidentiality. Okay, so encrypt and authenticate is not the way to go. Here's another construction. This is authenticate, then encrypt. So first authenticate, then encrypt. In this scenario, Alice has a message. Again, Alice and Bob share two separate secret keys, K1 and K2. Alice first computes the MAC of the message to compute some tag. Alice then concatenates the message with the tag and encrypts this all together to produce the ciphertext. And Alice sends the ciphertext on the wire to Bob. So this seems like a better construction and improvement. The tag is no longer being sent in the clear. When Bob receives this message on the wire, the ciphertext on the wire, the first step is for Bob to decrypt the ciphertext using the shared key, K1. This will produce the concatenated message with a tag. Bob can then recompute the MAC of the message using key K2 and check that the result matches the tag that was sent in the ciphertext. This one seems much better, and it is better than the prior setup, although in the general case, it is not secure. And this is because there are, it has to do with what is the encryption algorithm that is used. The ciphertext C may be malleable, meaning that the attacker can modify it in meaningful and useful ways, and may be able to do so in a way that allows the attacker to learn some information about the message. There are instantiations of this approach that are secure, so this can work, but it matters what encryption algorithm you use here. When we were talking about modes of operation, we were talking about encryption algorithms that were secure against chosen plaintext attacks, but not secure against chosen ciphertext attacks. And so those symmetric algorithms, we talked about the different modes of operation, those are, in general, those are malleable algorithms and would not be appropriate for use in this kind of construction. Okay, and so then the third construction is to first encrypt and then authenticate. And so here Alice has a message. She first encrypts the message using the shared secret key, K1, produce a ciphertext. Alice then computes the MAC of the ciphertext using the second shared key, K2, to produce a tag. And now Alice sends on the wire the tag and the ciphertext. So now it's okay to send the tag because it's not a tag of the plaintext, it's a tag of the ciphertext. And if the tag does leak some information, it's only leaking information about the ciphertext, which is securely encrypted. So this tag and the ciphertext and the tag are sent on the wire. Bob, receiving this, first has to compute the MAC of the ciphertext, checks whether the result of that matches the tag that came on the wire. If it does, then Bob will decrypt the ciphertext to produce the original message. And note that Bob is only going to decrypt the ciphertext if the tag is validated, right? So Bob does this MAC check first, and if the tag is invalid, Bob will not proceed and will not continue to decrypt this ciphertext that has been potentially tampered with. All right, we will stop here.